Come on, little YouTube.
But why? It would love to ruin your day.
There we go. Can confirm. I can confirm for myself now that we
You
exist.
have a Patreon hoodie.
Yeah, I know. And I have 4 of them. One for the sizes of each of the people in my house at the time that I picked them up, which was about 5 years ago. So I was traveling down the west coast of the United States as I do, with my
Yeah.
kids in tow,
Yeah.
and I sort of turned it a little bit into a work trip with them, but they had a
It's
great
what
time.
you do.
Yeah, exactly. So we went to Twitch and
Uh-huh.
got to hang out and check out the Twitch offices with Ashley Paramore and a bunch of other people from the Twitch
Yeah.
team. We got to go to YouTube and see the YouTube studio and meet our YouTube rep there and slide on their big slide and take a bunch of swag home. We went to visit. We hung out with Scott Manley
Yeah.
in San Francisco, and then we went to Patreon, which is also in San Francisco, and ate lunch with the team and sort of gave them an update on everything we're working on and had a great time. And then I forget. And then we visited people down in Los Angeles as well. So it was great. It was fun to just like, you know, and for the kids, obviously going and seeing
Yeah.
YouTube, right, was a huge thrill for them. So
Yeah. And this is where like the party that thinks shit is so cool is like, oh my God, I need to do stuff like that. But then the introvert in me is like, but that would require talking on the phone. And yeah, it's the stuff you pull off because you just ask people,
mhm.
hey, can I show up is
Yes,
really remarkable.
yeah, yeah.
And and kudos for just like asking. That's the hardest
Yeah, I
part
mean, it's
sometimes.
not a big ask at this point. All of the context that I have, I'm fairly familiar with these people at this point, right?
Yeah.
And so I'm able to just say, hey, we happen to be in the neighborhood. Can we stop by and say hi? And
Yeah. No, it's
they're
awesome.
always
It's
they're always
totally
super
awesome.
happy to say hi. So, because normally they live in this bubble, right? And they just don't get a chance to meet with the people that they work with on a regular basis. So no, it was
Yeah.
great, super fun. And then of course, obviously, best dad, right? Best dad ever. Almost as good as the time when we went down to the Penny Arcade Expo in Seattle and we got to meet we got to meet PewDiePie and Jacksepticeye and Markiplier, who some of the people who are watching this are going to recognize the names.
And this was at their height before any of them jumped the shark.
Yeah, yeah. Well, they're at various levels of. It's possible that one has jumped a shark or two, and the others are still on their meteoric rise. But it
Yes.
was great. I'm going to say hi to a bunch of people. Hi to Adam Synergy and Andy Cowley, Colin Jones, Coy Weniger, D Jamie 96. DPI 209, George Kalis, Giselle Sabarin, Gordon Dewis, Greg Nickel, Guido Bibra, John Seffield, Kylie Cerna, Martin Bradshaw, Mrs. Nat, Mr. Tom Harbin, Nancy Graziano, Paul Gracie, Pick and Duck, got a big crowd today, Raj Luthra, Rich Wilson, Ronald McCoy, Special Katana, Steve Chisnell, Susie Murph, Thomas Strupp, Sepp Strupp, Thomas Traniker, Wayne Johnson, and Zapfan. Hey, everybody. Um,
Hello.
this is going to be a tough episode for the people who are watching, who are going to be listening to it in podcast version. We're going to have to explain one of the most incredible pictures of that we've seen this year, just in words. So we're going to,
And the amazing instrument that got it. And
yep.
this instrument is one that required me to go find a photo.
Yeah, yeah.
Um,
Well,
yeah.
fortunately, we just did a video. I'm deep in the weeds on how this thing functions. So between the two of us, we should be able to drag this episode across the line. Now, before we get into it today, did you see the new pictures of
Beetlejuice.
Beetlejuice?
Beetlejuice.
I know, I
Beetlejuice.
know, I know. So let me pull this image up so I can show people.
I startled the dog.
Yeah.
It's no longer symmetric. We don't
Yeah.
fully know what's
Yeah.
going on, but
So let me just bring this up and I'll show
Hi.
you can see the picture as well, Pamela. So you sort of see what people are seeing.
yeah.
So here is, you can essentially see the comparison from before till now. So here it was. So what it is essentially the biggest, most powerful telescope on Earth, the Very Large Telescope, happened to be observing Betelgeuse with the Sphere instrument, which is probably the coolest thing that is attached to the Very Large Telescope. It's the gadget that finds newly forming planets orbiting, in brand new star systems. And so it took this picture of the star. And then, because they had this image already banked, they came back around as it was dimming in December and took this second image. And as you said, it is dramatic. In the one, it kind of looks like a sphere.
More or less.
More or
round.
less. And then on the right, there's clearly a big bright spot up towards the top, but a dimmer spot down below. And that definitely will partly explain how the star is looking a lot dimmer than it normally does. So
Now, this image release did not come with a science paper. The science quote in the release said that they're pursuing two different explanations.
Yeah.
One is dust. The other is just intrinsic issues with the inside of the star. Time will tell. What has me so frustrated is we aren't that far from losing this object out of our evening sky. And this means no one on the planet will be able to see it for several months.
Oh, because it is going to be going behind the sun. Right. And so it could explode and then we come back around and there's just shrapnel on the other side.
Well, it will be a daytime object unless it's so close to the sun when it goes boom.
Right.
But the day-to-day variations that we're all currently enjoying watching so much.
Yep, those go away. Yeah.
But I mean, still, we're not, we're not looking for it to happen for probably another 2-3 months before it starts to really go into the daytime in behind the sun.
Yeah.
And there's still some spacecraft that can make some observations. And of course, even Curiosity could watch and see what's happening if need be, right? Which would be kind of cool.
I don't know where it is in Curiosity's sky. I mean, the problem is Curiosity is just another object on a world that has days and nights.
Yeah.
It'll mostly be visible to Hubble. The issue will become it is an equatorial object, so it will be very close to the sun for a period where it's even unviewable to Hubble.
So I just want to remind everybody as well that I'm doing another live premiere of my latest episode right after this show. So once again, when this episode wraps up, come and join me over on my YouTube channel, where our latest video is all about the weight calculation, which is, should you fly to, hop aboard your multi-generational ship to go and settle Alpha Centauri, or should you wait so that a warp drive spacecraft doesn't pass you by and need to pick you up? And in fact, there's a very specific, very good calculation that's been made to figure out what is the exact right date that we can anticipate how long you should wait for before you actually hop in your spacecraft and leave.
That's wild.
Yeah, so that's going to be that'll be after this. So still stick around.
I love the optimism that warp drive will happen.
Yeah, well, that's the point. I'm losing some packets from you. Are you uploading something, syncing something?
No, let me go through and make sure I don't have any evil windows open. This is me. I will need that window later.
Yeah, it felt like your computer was hiccuping, but...
You know how sometimes you end up with like 40 tabs open because you want to read something later?
Oh, I'm staring at it right now.
Okay.
For me, that's half of it, and then the other half of it is that I'm working on some article, and so I've got all of my research all, splayed out in front of me, and then have to close these windows one at a time, at the end of I got to remember to do that. Otherwise they just continue to clog it up.
Yeah. And this morning while trying to write our Daily Space episode, and if you aren't subscribed to the Daily Space, you're missing out on a daily news podcast.
Yep.
Yeah, this morning it was just like the breaking news just kept coming. And did you happen to open up the papers tied to the New Horizons science articles?
No. Is that the one about that the formation of the solar system seemed to have gone
Yeah.
a little bit more slowly than we had anticipated?
That's one of the papers.
Yeah,
The
okay.
one that's on the geoscience and geophysics of MU69, I'm actually a co-author on.
Oh, incredible. Congratulations. That's awesome.
So I just wanted to squee happily.
Yeah.
Okay, reopening Patreon, and then I'll be good to go. Our packets happier?
So far, yeah. You're still
Okay.
yellow, but you seem to be moving around okay. So
I suspect the yellow is more due to the hue light bulbs.
no. Sorry, the yellow I'm talking about the quality
packet
of your packet. So it's not red, it's in a yellow, and now it's back to white. So I think we're okay.
Okay, I will stop moving around.
Okay, so let me know when you're ready to press record. Oh, Annie says there is no launch. I repeat, there is no rocket launch.
It is true. It is true. They have scrubbed for the day. Sunday, we are going to have another Falcon launch with another group of Starlink satellites.
Yeah.
So there is.
So
that
apparently
coming.
some people were saying that they had to decide whether they're going to watch my video or the rocket launch. And I just
And now they don't need to
I couldn't let that
decide.
stand. So I had to get them to push that rocket back.
You can always do picture in picture.
Yes, watch both. And it's a short episode. It's only 10 minutes. All right, let me know when you're ready
Okay.
to roll.
I am pressing record. It said F you. Hold on. My computer has too many opinions. What is today's episode number?
It is 559.
I am now recording correctly.
Yay, me too. All right, here we go. Astronomy Cast, episode 559, The Surface of the Sun. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well, and I'm so pleased to say that since our last episode, when we said that we're looking for help with CosmoQuest's open source project,
Mm-hmm.
I've had a number of Astronomy Cast people show up on CosmoQuest's Discord, and we're pulling together a great group of humans. So thank you, all the humans out there interested in helping us with CosmoQuest.
And let's say a person didn't hear that first call for help and may still want to throw some code into the, I don't know, my analogy is falling apart here.
GitHub.
Into
Falling
the
into the GitHub.
Yeah, throw
Yeah.
some code at the GitHub. How can people get involved?
The best thing that you can do is go over to cosmoquest.org, click on the Discord link, and say hi in the Volunteers Reporting for Duty channel, and we will add you to our coders group, add you to the GitHub repo, and off we shall fly, open source away.
That sounds great. All right, so a brand new telescope has been completed on Maui's Haleakala, and it has just one job: to watch the sun in unprecedented detail. It's called the Daniel K. Inouye telescope, and the engineering involved to get this instrument operational are matched by the incredible resolution of its first images. And I think we need to apologize in advance to everyone who is listening to this episode conveniently as a podcast, because I'm probably going to be showing some pictures. We are going to be talking about one of the most incredible images of the sun that has ever been taken. And so I think the hope here is that the listeners are already familiar with this image, and now they're waiting for their favorite astronomy explainers to follow up and give them some context to what it is. But if you don't, I'm sure we'll have a link in the show notes. Search for sun surface picture on Google, and you will have this incredible picture. If you get hungry for caramel corn, you are looking at the right image.
And if you go find it on YouTube, you're just gonna like want to stare at the sun's surface with
Yeah.
this telescope, not with your
Yeah,
eyeballs.
it's
kind of
so
forever.
beautiful. That's a Bug's Life reference. Okay, so let's talk about this picture. Let's talk about this
Okay.
telescope. Where should we start?
Let's start with the telescope.
Okay.
Well, it's hard to talk about an image when you know nothing about the telescope. One of the things that we've brought up over and over and over on this show is you can get higher resolution images by using telescopes with a larger diameter. You can do this with interferometry, you can do this with larger collecting areas. And to date, we've never gone too gung-ho collecting light from the surface of the sun, because the sun is a giant, hot, boiling ball
Right.
of plasma, and its light can melt things.
Yeah, and then when you concentrate it with a mirror, as we have seen with what you do when you have a magnifying glass,
Yeah.
you turn this sunlight into a laser beam.
I have inadvertently started fires twice with telescopes looking at the sun.
Yeah, I have merely destroyed a telescope.
Oh.
Yeah.
I've been very good about not destroying telescopes. It's
Yeah.
just the things around them I keep setting on fire.
I'm not sure which one is worse. I'm going to say that what you've done is worse than what I've done. I've merely destroyed a $200 telescope. You've tried to light a house on fire.
A piece of paper and some carpeting.
Yeah,
But
that's funny. Right. So trying to magnify the light from the sun is madness. And yet, in order to see detailed images of the surface of the sun, you want to magnify the image. How can this be done? What wizardry?
Wizardry is the correct answer. So every single aspect of this telescope is designed to make this system as safe as possible and to prevent any excess heat. This means that the dome has a unique design where instead of having the normal roll up slit that leaves this big stripe of opening into the dome, they have a circular annulus that opens up that is matched to only let in enough sunlight to illuminate the entirety of the 4-meter mirror that's on this telescope. So they start by restricting how much light gets into the dome.
Yeah. So they and so just before you continue on, I think it's like what, a 4.2 meter mirror.
Yeah.
That's a big mirror. I mean, it's not,
and it's super thin. It's 75 millimeters thick.
Right.
So this is a system that they can do adaptive optics with, and it's also thin so that it doesn't overheat.
Right.
This is one of the amazing mirrors that came out of the Mirror Lab in Arizona.
Right. And so it's got these actuators underneath the surface of the primary mirror that allow it to make minor distortions and try to compensate for the atmosphere that's above it. So you've got this enormous amount of light going into this 4.2 meter hole on the side of this observatory, bouncing off of this primary, getting focused.
Now I do have to step back and say that while the mirror is more than 4 meters in size, they're only utilizing 4 meters of the mirror.
Mm-hmm.
This is a design where they're not going all the way out to the edge when they use it.
Right.
And they also are focusing it in a kind of crazy way, which is also part of why they're not using the entirety of the mirror. They didn't want to have to put anything in the path of the sunlight.
Right.
So they have the light coming in through that exactly sized hole in the dome of the telescope. The sunlight goes through that hole, hits the mirror, which is tilted and shaped ever so slightly to direct the light out of the side of the incoming light. So the light comes in, bounces sideways,
Right.
gets focused onto a secondary liquid cooled metal donut of a
Yes.
system.
Yeah, they call this the heat stop.
And this incredible system eliminates 95%
Right.
of the heat. This prevents them from melting anything further down.
Right. And I think that the thing that's really important, so a couple of things there, as you're saying, right? Like with a traditional solar telescope, you put the block, whatever you're going to use to decrease the brightness of the sun, you put that in front of the main hole on the telescope. So if you've got a Newtonian telescope, you put it in front of the entire, before the light can even get inside your telescope, you've already shaded it.
They're not doing that.
And they're not doing that. They're waiting. And so the reason, if I understand, is that they don't want to have even like slight problems with whatever filter they would have to put in front of it. That would decrease the quality of the image.
So their goal is to remove anything that might create contrast issues, remove anything that might create optical aberrations, remove basically anything extra that they don't absolutely have to have. Now, once they've gotten down to 95% of the light coming in from that 4-meter mirror, so they're keeping the resolution, reducing the amount of light. I'm knocking things off my desk. Sorry about that thunk, everyone. Let me say that again so that Susie can remove the thump as my hand gestures became too big. So the light comes in. They have 95% of the light from all 44 meters of the telescope going up to this donut. So they're keeping the resolution and throwing out unnecessary light so they can still do all the science they want and get maximal resolution out of their detector.
Right.
Now, at this point, it starts to act more like a normal telescope. They're shooting the light down to what's called a coude focus. This is where you have some sort of a split that takes the light and moves it from that room that your telescope is living in and generally shoots it to the basement somehow.
Right.
Lots of telescopes do this in different ways. The 107-inch telescope at McDonald Observatory, which I've used the coude spectroscope on, it shoots it through the pier of the telescope down through the floor and into a different room using mirrors. The Hobby Eberly telescope, it uses fiber optics to do this. Lots of telescopes nowadays are accomplishing this with fiber optics. They pick off the light, move it through the cables, get it into their big basement room. Now, the reason you're using this big basement room is so that you can have massive instruments to spread the light out, to create spectra, do all sorts of amazing stuff. And normally you have some sort of rotational system to keep things fairly aligned, but you're looking at stars, so you're not looking for too long and you're not worried about rotation too much. They're looking at the sun
all day long.
Entire day.
Yeah.
Yeah. And so they do what I consider to be one of the most crazy, awesome things I have ever seen done with a coude room. They're rotating the whole darn room.
The whole room just turns
Yes.
to keep the
Yes.
instruments aligned with the telescope and everything that's bouncing around.
This is a 150-ton platform of instruments
Yeah.
that they are precisely rotating as they track the sun. So their tracking isn't just moving a 4-meter telescope. Their tracking isn't just moving very precisely a dome, and domes normally don't have to move precisely. They have to track the dome precisely, track the telescope precisely, and track the 150-ton coude laboratory precisely. This is remarkable engineering. I can't imagine what the construction company they went to originally thought when they were asked, can you make this entire room track the sun? Yes, they could, but probably not anything anyone expected they'd be doing when they got their mechanical engineering degrees.
Oh.
it's a feat of engineering.
Yeah, it really is. One of the other feats of engineering is just temperature control. I mean, again,
Yes.
you're bringing in, I think it's like 12 kilowatts of energy nonstop, continuously just bringing in enormous amounts of energy into this enclosed space, and you have to get rid of it.
Yeah. And they do this through a variety of ways. They have, first of all, extra air gaps, in this case, rooms between the dome floor. And then when you get down to the instrumentation, having extra rooms, well, it's sort of like having storm windows in your house. Those air gaps provide a place where heat gets dumped and then doesn't get transferred. And then they just are coolanting everything. That donut, I'm just going to be in
Yeah.
awe of
Yeah.
for a
So
while.
if you look at the outside of the actual shutter, the outside of the dome, they've got these flappy shutters that
Louvers.
that are all across the outside of it, and so they can do a lot of really sort of high in very quick response temperature control. They make ice in the observatory at night when it's cooler on the top of this mountain, and then they pump it through. They use this as a way to run coolant through the entire system. There's like 7 kilometers of coolant piping throughout this entire instrument. So again, and as you said, they have all this air gapping inside that they can then also use to try to maintain the heat. And so the goal is to just that every single part of this entire telescope, from the mirror to the instruments, all the way down to the ground level, the whole thing is precisely the same temperature all the time.
And that is really the key. And this is a problem that we've been trying to solve with telescopes for a while now. Once our telescopes got good enough, we realized air is the enemy, because if you have temperature variations in the air, each of those temperature variations will bend the light. Air can act like a lens. It's super annoying. Now, with a regular everyday telescope, you open the dome, you turn on some fans, you make sure all the doors are open, and you're good enough. But as we've started building bigger and bigger telescopes, they've had to start figuring out how to add all of these basically Venetian blind systems that open up and circulate all the air. So all day long inside these nighttime telescopes, you run air conditioning to try and keep the room at the temperature you expect the nighttime to be. Well, here they're flipping that on its head, and they're trying to keep everything the temperature it's going to be during the day and not have any greenhouse effect going on. So just like our cars will heat up in the sunlight, domes will heat up in the sunlight, and that would be death.
And you're bringing in all that
system's
heat.
Accuracy. And you're bringing in heat.
Yeah.
So essentially, they're bringing in heat, and they have to constantly prevent that heat from heating up the air. And it's not easy, and they have figured it out.
Yeah.
And this is where I think we should start talking about these amazing images.
Let's do that. And so again, if you need to pause the podcast, go get yourself in front of a browser and take a look at the pictures that this incredible telescope has taken. And so now, assuming that you have done this, or you're kind of familiar, or you're just going to sort of follow along with us, tell us, and I'm going to show the picture for the people who are watching this as the live stream, but tell us kind of what we're looking at.
So the image that this telescope produced is a series of hot cells that are yellowy in the center, fade out, and then are surrounded by inky black darkness. Now, the crazy thing is that inky black darkness is still super bright. What we're seeing is slight temperature variations in the surface of the sun, where convective cells of hot gas are rising up, and then through the center they're rising up and then cascading down as they give off their heat to outer space. And because luminosity goes as temperature to the fourth power, the very small temperature variations from the center of these convective cells out to the cool edges of these convective cells, well, they have amazing differences in luminosity that, because of the limiting contrast of what we can do with images and eyeballs, we perceive as dark outlines around bright cells.
And so, sorry, so like the bright parts that we're seeing,
Mm-hmm.
those are the hottest parts, the parts where the sun is actually blobbing out its convective material from the interior, and then the darker regions are still insanely hot,
Yes.
just less hot than the actual bright surface.
And what makes these particular images so remarkable, it is each of these convective cells is roughly the size of France or Texas, which are remarkably about the same size, but Texas is bigger. These convective cells on the sun are the size of France or Texas. And we can make them out not just as like a few pixels across, but as not literally gazillions, but as a lot of pixels across, because this instrument can resolve features that are just 12 miles or 20 miles in 12 miles or 20 kilometers in size.
Yeah. So the little, if you like really zoom in on the image and you can see individual pixels, these are on the order of 12, as you say, you know, like 20 kilometers across. And when you think about the fact that we're seeing these images from 150 million kilometers away, it's just an incredible feat of engineering and astronomy to be able to do this.
And the entire field of view for this telescope is measured in arc seconds. This is an extremely high resolution system. We're never going to get full disk of the sun. Heck, there may be sunspots that come up that are bigger than this telescope can see. But with this kind of resolution, even now in its engineering phase, we're seeing things that when you try and look up information on them, current publications say can't be resolved, not well understood, bright things.
Yeah.
Faculae are what I'm thinking of here. We know that there are magnetic effects that occur in those dark boundaries between individual convective cells, and these bright magnetic effects aren't well understood. And this may be how we finally are able to understand them. This telescope is still in the process of being commissioned. We're talking about it now because we're getting amazing images off of it. And the time is right to say, photosphere, here we come. The top 50 miles of the surface of the sun is about to be ours to understand in detail.
So then what is the point? Now, obviously, it's incredible to see these high-resolution images of the sun, but what is it good for? How does this make my life better?
Well, it's hopefully going to help us better understand solar weather, better be able to make predictions of what's going on. The top layer of the sun, while generally kind of ignored because it's not as striking as the higher up layers, this photospheric layer, it varies from hot spot to cold spot between about 4,500 degrees and 6,000 degrees Kelvin. That's 4,200 to 5,700 Celsius. And the effects that occur at this level lead into bigger and bigger effects as you go up in the sun's atmosphere. The faculae that we see as bright nothings at the surface of the sun, at the photosphere, end up growing into bigger and bigger things called phages as you get higher up in the atmosphere. These can end up forming coronal loops that in the outermost layer of the sun, these are the big magnetic loops that we see that when they let loose can blast particles our direction that take out communication satellites.
And that's like, if you want the real practical advantage for observing the sun at this level of detail, advance warning of a solar storm that's going to cause a serious disruption to our modern interconnected human society is the benefit that you enjoy, is some advance warning. Like right now, what do we get? Like 2 hours of notice that there's a significant solar storm inbound because we're starting to detect the first particles smashing
hitting
into the
solar
Earth.
dynamic. Well, we also, so this is where solar dynamic orbiter has so far played such an important role. This little spacecraft that is sitting out balanced between the gravity of the Earth and the sun, close enough to the sun that particles hit it, and thanks to the speed of light being so much faster than the speed of particles, it can go, Earth, there's stuff coming.
Yeah.
And we can safety things. We can send astronauts for cover if we need to.
Yeah.
And that early warning is amazing. Now, what would be even better is predictive models. This is the difference between looking at radar right now and seeing a tornado on radar heading towards your house, and having satellite images that allow you to predict a potentially dangerous storm is brewing.
Right.
Now we use spacecraft to predict weather on Earth. Well, now we're going to use Earth-based telescopes to predict weather on the sun more effectively than we can do with spacecraft. And I love this interplay of how we really need all these different kinds of observations to make sense of what we're learning.
And the hope here is that we'll get a couple of days of notice, that astronomers will see these features on the sun, see them brewing, see a burp forming on the sun that's going, and understand how all of these pieces are connected, right? When you look at that picture of the roiling, bubbling surface of the sun, how do you know that any one of those areas is about to cause a coronal mass ejection? It's just, you just don't. And so, but being able to sort of track back and use, as you say, these predictive models of the sun, we'll get to this point where suddenly now astronomers can look at all these regions and go, okay, you know, you wouldn't have known before, but now we do know that this region right here that is slowly rotating towards the Earth, like the Death Star, is about to let off a blast that could cause us a problem. And so unplug the electronics that you care about, you know?
And what's more, as we're looking to start putting human beings in space outside of the Earth's magnetic field, Moon, Mars, wherever, we may only have a small volume of space that is adequately protected from radiation that they can stay healthy if their spacecraft gets hit by a burst of energy from the sun. Having this kind of predictive model will tell them perhaps ahead of time, hey, maybe you want to come back to the Earth a few days earlier if you're on the moon. Hey, get ready to go into hiding as you're on your way to Mars. We are lucky to have our magnetic field. And so we, first of all, need to be afraid, just like you say, of another, what we call a Carrington event, a massive burst of energy from the sun capable of doing bad things to our power grid, to our satellites, to our astronauts in low Earth orbit. We also need to be able to predict what's going to happen at the moon, at Mars. All these things are necessary to keep the science flowing and the humans alive.
Well, and I want to know when I should go and see auroras.
Well, yeah,
you know,
that's true too.
Right now, all we get is we get a couple of hours of warning that there's auroral activity. Not even, we get, you know, there's auroral activity right now. Well, it's too late for me to book my trip to Iceland. But if I could get 2 days notice that there's going to be a big storm coming, then I can book my trip to Iceland and go and enjoy really powerful auroras. I
was going to say road trip to Canada, but sure.
Sure, that place, yeah. It's a big country. It's easier to fly to Iceland than to road trip in Canada. And it's
probably true.
Much better equipped than, you know, Northern Canada is a hard place to be. While I gotta say, being in Iceland is a quite luxurious experience. I quite liked it. Even in the wintertime, right? Wintertime in Iceland is delightful compared to wintertime in Canada. Still on the bucket list. Yeah.
Still on the bucket list.
So, I mean, all we've seen right now is the first light images. Chances are, you know, you're going to get bored of, because every image is going to kind of look like this, just different flavors of variations on roiling plasma on the surface of the sun. But we are going to see sunspots and other interesting features over time as well. So
now
stay
this
tuned.
instrument won't be fully built until this summer. They're aiming for having all the spectrographs, all the polarimeters, all of the devices that will allow us to study even more effectively the outer layers, the temperature, the magnetic fields this summer. It's coming.
Yeah,
We
so
just have first
more
light.
instruments coming. So stay tuned. Right on. I'm super excited about this, and I did a video on my YouTube channel as well. So if people want to follow even more information, they can follow that there. Pamela, do you have some names for us this week?
I do. As always, we are brought to you by you. We are so grateful to all of our
recursive.
Patreons. Well, it's true.
Yeah.
It's true. We are so grateful to all of our patrons over on patreon.com/astronomycast. If you can support us, please do. If you can't, we totally get it. Just leave us a review somewhere. Help people find our show. We're good. So I really want to thank this week Jordan Young, Buri Gowan, Frada Tanbao, Ramji Ananthu, Andrew Palestra, David Troig, Brian Cagle, The Giant Nothing, Laura Kettleson, Robert Palesma, Corey Diwali, Paul Garman, Les Howard, Joe Cunningham, Emily Patterson, A Blip in the Universe, Infinitesimal Ripple in Space-Time, and Ed.
Awesome. Thank you, everybody. And as always, Pamela, thank you for bringing the knowledge, and we will see everyone next week.
Sounds great.
Bye.
See you all later.
Don't go anywhere.
Don't go anywhere.
All right.
And now we save. Okay.
559. So did you see that Skylius has gotten into the dog collection?
Yes, she
as well.
She has a greyhound and a whippet puppy, and they're adorable.
So cute, yeah. I think her new live streams are just, doing some science and then pointing the camera over at these adorable sleeping dogs, and then back to the show. Yeah.
Science is better with dogs.
I'm sure our single dog household is just a countdown to another one. All right.
Dogs are happier when they have a pack.
Yeah, they definitely keep tabs on the whole crew. All right, so we're going to do some questions for about 17 minutes or so, and then, like I said, you're all going to come and join me over on my YouTube channel and watch my brand new episode about the weight calculation.
WAIT.
WAIT, yeah, not the WEIGHT. Steve Chisnell says, I'm still wondering whether a strong enough solar flare could compromise Earth's protection from UV radiation or even threaten the integrity of Earth's atmosphere as a whole.
Only if our sun was suddenly replaced with a baby red dwarf star and we were much closer.
Yeah.
Our sun isn't that dangerous. We're good at that level. It's not going to wreck our integrity. It may wreck our electrical grid.
Right. Yeah.
And that's strictly because it will oscillate the magnetic field of the Earth. And it's the oscillating magnetic field that will drive the generation of electricity and power lines that will then overload the power lines and take them down.
Yeah. So before our modern electrical system, the Earth was immune to the most powerful solar flares that the sun can ever send.
They just scared the bejesus out of people because of aurora.
The best you get is suddenly people in Jamaica get to look up and go, wait a minute, what are these green lights in the sky? Every couple hundred years they get to see aurora as well. In Canada, we get to see several of them every year. But it's the electrical grid getting the electrons pushed one way, then the other, back and forth, overloading circuitry and various pieces breaking. And so we made this problem.
It's okay.
Yeah. Yeah, but when you think about how long life has been around, how long the atmosphere has been around, everything's fine. Annie asks, what filters were used to take the image of the sun? So did they...
They're using V and B. So let me pull up.
VNB?
Yeah, so green and blue. Let me pull up the exact wavelengths if I
Unc Willie is
can.
saying it's 789 nanometers.
That so the blue channel is order of 400 nanometers to 500 nanometers. The red channel is order of 650 to 700 nanometers. And they're looking at specific filtered regions within each of that.
Right.
So, for instance, they let through on the blue channel the calcium, the H beta. On the red channel, they're letting through the H alpha, titanium, iron lines.
Right. Let's see here. Colin Jones says, does the unbalanced Betelgeuse make us wonder if it swallowed another star?
So if it swallowed another star, it did that long ago. There are some papers about that. It hasn't recently swallowed anything. We would have seen it in earlier observations.
Yeah, I think it's really important to say that when you look at those pictures of Betelgeuse, and I'll put the picture up right now so you can so people can see it again. It looks like it's like blobbing out, like it's got like some kind of big lobe, but that's not necessarily what's happening at all. It's just that part of it is bright and part of it is dim. And the part that could be dim, the part that's down and to the right, that I'm holding my mouse over for the people who are watching this, there could be a big cloud of dust that's in front of this portion of the star, and so it's just not looking as bright as the rest of it. So
can you bring up the dust image with the occulting disc?
Yeah, sure. I'll show you the screen as well so you can see it. So that's the one image, and then the other one that they took was with a different instrument. And it's kind of a cool story. So this image here, so you're seeing the disc, this right in the middle of this disc is, they put the star back from the other picture. So they photoshopped in the actual star Betelgeuse in the middle of this black circle, just to give you a sense of perspective. And so all of this is infrared of the dust that's surrounding the star itself. And these are all layers of material that were thrown off in the past. It's constantly just disgorging its outer layers out into space. And it's very cool. The instrument that's using this was designed to search for planets at Alpha Centauri.
It's just a really cool system.
Yeah. So let's bring that back. So, but no, there's no reason to believe it gobbled up another star.
Life is good.
And it is not necessarily that it is actually a physical bulge. It could be a convective cell, but it's more likely just it's a brighter spot on the star. YouTube Zero Admin on Twitch, who was on our live stream yesterday with Skylius, I saw you in the chat, asks, do we know more about the center of the sun or the center of the earth?
We know more about the center of the earth because of earthquakes, allowing us to do seismological mapping of the interior of the planet.
Yeah.
We can start to do some of that with the sun, doing what's called helioseismology,
which
using
is like
the Gong observatories.
Term. Yeah.
Yeah. But with the earth, we're on it. And our planet has all sorts of tectonics that aren't that generate waves that you can see how they propagate through, and because they're non-repeating, it's cleaner observations in some ways for some purposes.
Ben Kalo was asking, was that animation time-lapsed or actual speed? So from what I understand, it's a few minutes. Someone was saying it's about 10 minutes of activity into a 1 second-ish, 2 second-ish clip.
You can watch through a telescope the sun change, but it is slower than what that video showed.
Right.
It's just cool that you can watch a star change through a telescope.
Dying Atheist is noting your cool necklace.
Oh, thank you. I got this a number of years ago at a one of those global free trade stores. It was made and purchased from an artisan in South America.
Does it have anything to do with space?
No, but it looks like it does.
Yeah.
Which is kind of why I love it. So it just has all these spacey patterns on it.
Cool.
And silver's considered prettier when it's tarnished, all you people who are thinking I need to clean my jewelry.
Brandon Kelly says, would a tactical nuclear weapon detonated in Titan allow temporary, easy access to the ocean below? Detonate, then drop drone subs into the new chasm.
No.
But I mean, you are definitely thinking big, Brandon. That's we do like the scale of your dreams. You are thinking about how to get there from first principles. So
Titan may have subsurface oceans, but it has surface oceans.
It has both surface oceans
the surface
and
oceans of Titan. It's alcohol.
Yeah.
That stuff burns. No.
Well, you need to bring the oxygen though. So, yeah, I mean, it could very well have 100 kilometers depth of ice. So even a really powerful nuclear weapon
not going to get
isn't going to dig through 100 kilometers of ice.
It's not going to make that big.
Yeah. So.
And if it could, it would disrupt the core of Titan, and that would just be like never-ending story kind of solution.
Yeah. So. Sorry. And people noting
that was
in the chat.
A very Canadian sorry.
Yeah, that's a full-on Canadian sorry. Yeah, I'm sorry, Brandon. We cannot sign off on your plan to drop a nuclear weapon on Titan to try to sample its water. Matthew Lear is asking, where is Jupiter and Earth to scale on the Betelgeuse photo? So,
Betelgeuse, I want to say, is the size of Jupiter's orbit.
Size of Jupiter's orbit, yeah. So, you can't even really see Jupiter that well when you're seeing the entire Jupiter orbit.
Yeah.
And then, of course, compared to Earth, it's ridiculous. Don't even. Yeah. Let's see. Any other questions? DJ Me 96. I understand that protection against solar storms has something to do with politics too. How is the current situation in the EEUU? Are there protocols? So, are there really any kind of international protocols on dealing with? That dog really wants to participate in this show.
Picked up.
Yeah. Pick me up. I'm a lap dog.
She's used to getting to
now we're just gonna encourage it.
She's like, no, I'm not gonna jump up now. She really wants to go back. We were sitting downstairs in my wingback chair earlier, where she could cuddle against the radiator while sitting on my feet. It's cold. She's skinny. She just likes the cold. But I have to admit, I don't know if there's any international policies on solar weather. I just don't. I know that there's generally sharing of data because scientists like to share our data. We're kind of nice that way.
I see the National Space Weather Strategy and Action Plan from the White House.
Oh, okay, now.
Yeah.
I know the IAU has working groups on stuff like
there's
this.
a global aviation space weather network that's been launched to try to do that. And so part of it, I think, is that we just don't have enough warning, right? The warning is duck and cover, right? The warning is, hopefully you'll be able to buy new stuff after it all gets wrecked. But you can absolutely anticipate in the future that there would be this moment where
where we get this 2 days worth of notice, and there's this international understanding, like, okay, let's disconnect the, all of the power lines between these two regions, and these sections go on, and airplanes airplanes will be grounded until the space weather has passed, and satellites get put into safe mode. And there's all kinds of precautions that we can take when one of these events is about to happen, especially a really bad one. And we've seen, like, apparently they happen once every 25 years or so to the Earth. And the last one that we saw, there was a really bad one that happened back in Quebec during the winter time. I think it was back in 1989, and it was bad. Like, the power grid just fried for a huge chunk of the province at the worst time of the year for that very cold province. And our power grid is so much worse and more interconnected now than it was back then. So I think if we actually get notice, then I can absolutely expect there to be these international committees coming together to agree on what must be done when we can detect some bad space weather.
But there is a difference between working groups trying to figure this out of scientists, which do exist, and there being legal agreements between nations, which are often much harder to come up with. Luckily, corporations, who are the ones that get affected, because this comes down to their financial bottom line, they're often willing to work with the working groups and just everyday scientists.
So Unc Willie is saying, did you see the video of the dog greeting astronauts?
Oh, the astronaut. Yeah, that is quite
Christina.
fabulous. That was a very happy, skinny little tail wagging dog.
Yeah, let me see if I can find the. I'm gonna post the video here. Hold on, see if we can see here.
So this is.
Let me start from the beginning here.
She was in space for the longest of women, the second longest for an American. And the dog is like, Dad, oh my God, Mom! Wait, Dad, Mom! It is one of the more wholesome things on the internet, more of this.
That is awesome. So cute. All right, we're reached the end of our time here, and I, like all of you, have an appointment now to go and watch my brand new video over on YouTube. On my YouTube channel. So hopefully someone will post a link to the episode, because I'm logged out of my normal YouTube channel. So I've got to wrap up this episode, switch over to my YouTube channel, and then I'll be there and hang out with you, with everyone while we watch the new episode, all about the weight calculation. So if you want to do that, you can do that now. Before we go, a huge thank you, of course, to all of our friends who are watching, all of the moderators, all of our patrons.
Annie, who's hosting us on Twitch.
Annie, thank you for watching this episode, and then she's transcribing it all to Twitch. She's doing some kind of interpretive dance,
pretty much, yeah,
to show what's happening on Twitch. So thank you, Annie, and thanks to everyone watching on Twitch. You're not forgotten. So again, go to my The Universe Today YouTube channel, and we'll watch an episode. All right. Thanks, everyone, and we will see all of you next week.
Bye-bye.